All right, welcome back to CE 528. In the last class, we were talking about how it's really difficult and a lot of issues that come up when you're trying to relate all the inputs that you do, that you use to create the roads or whatever output that you want to create, and translating that into a dollar amount or a currency amount is fraught with challenges. And we talked about some of those challenges in the last class. If you want to rewatch lectures from that, like, there could be joint costs, there could be, issues of who pays, there could be multiple payers in the mix, there could be foreign exchange issues. But if you can somehow, some way, translate your resources into a dollar amount, which I think in the most developed countries we should be able to do. I mean, in the context of transportation, there is still problems there, but you should be able to at least come up with an overall cost function by looking at all the inputs that are going in and multiplying that by the unit prices. You should be able to come up with this cost function, supply function. Now, you should remember how that works, and you should remember all those challenges. But when we solve the problems, we are going to assume that, yes, we are in fact able to do that. We're in fact able to take the prevailing prices of capital and labor and bulldozers or whatever we want to bring in to serve our needs to build a road or whatever we're building. We should be able to convert that into dollars. And once we can do that, that gets us to what we call, that gets us from the production function that we showed you before to the supply function that we are going to talk about now. So, and this is something that you are going to have in your homework problem. So let's pay close attention to that. So your next homework problem is going to be based on this. We're trying to find the expansion path. The idea of expansion path is, if you want to build, if your budget goes up from $300 to $400 to $500, how much road you should build every day, and what should be your expansion path. Now, to find the expansion path, you start with, in this figure, if you go back to what we talked about in the last class, so let me kind of take you back real quick to that slide. Remember this. And now I have a smoother function, okay? So I showed you the sort of a discontinuous function of building the road. And we said, what did we call? What did we call these lines? Do you recall what did we call these lines? Anybody remembers from last class? The line that I just traced out over, that I traced over. You remember what these lines were called? We called them something. Yeah, isoquants is exactly right. Isoquants. Isoquants means, iso means same, quants means quantity. So it's the line along which same amount or same quantity of road is produced by using a mix of bulldozer and workers. Okay. Now I have the same thing here. I have the same thing here. In this chart, I have the exact same thing. But now instead of having those curved line or discontinuous function, I have what I'm going to call continuous function. Okay. So these are what the isoquants is. So this is where you start. You come up with the isoquants, basically the combination of bulldozer and workers, that gives you the same amount of road. The bottom isoquant is for 1 kilometer of road, the middle one is 1.5 kilometers, and the top one is 2 kilometers. Okay. Now, the next thing I'm going to do is, I'm going to come up with, so here is all the assumptions. Where do they go? This right here is where all the assumptions go. The price of labor and bulldozers. It's $10 per worker per day. And I know it's absurd, obviously, but let's go with some numbers, right? I needed some numbers, so I'm just throwing in some numbers. And it was as absurd as when I created these notes 5 years ago, 7 years ago, whenever. But it doesn't matter what those numbers are. But as long as those numbers are there, you could figure out your budget lines. So let's say if the labor costs $10 per worker day, and one bulldozer costs 200 bulldozer day, you can come up with these green lines. You can come up with these green lines that I'm going to draw now. And I'm trying to trace over those dotted lines just to show you. Maybe I'm not perfectly there, but you could see. Now, what's so special about these lines? The new green lines that I've drawn. What is so special about those green lines that have just traced? Any thoughts on what is so special about those green lines that I just traced out? I'm going to do something here. Maybe that'll make it easier for you. Does this blue line give you an idea about what's so special about these green lines that have just been traced out? Any thoughts? Pause the recording if that's something you prefer. So a very good response in the chat that basically these green lines represent all possible combinations of number of workers and bulldozers that cost total $300. The first green line represents $300 cost. So all possible combinations of labor and worker in which you can spend $300 on. And then the second line represents same thing for $400. How can you spend $400 on labor and bulldozer combination? And then the third one represents same thing for $500. Okay. Now, you could spend, so it's very clear that you can spend $300, $400, or $500 on a bunch of different combinations of workers and bulldozers, right? That's clear, right? If that is clear, what is so special about the points that I'm going to spotlight just now, okay? I'm going to try to spotlight some points. What's so special about these 3 points that I'm spotlighting in blue right now? Pause again, give you time to do something recording. So the special thing about these blue points is that at these points, the cost curves, the straight lines, the green straight lines are tangent to my red isoquants. Okay? And that's very important because if you choose any other way, to spend $300 or $400 or $500, would you get more road or less road for that money if you go on any point that's not tangent to the isoquant. Yeah, you will definitely get less road for the money unless you are sitting at that tangent point that I'm marking with the blue dots here. So essentially what's happening is that if you want to find out what is the best way as your budget goes up, what is the best combination of labor and worker that you should use, you should be looking for the points at which the cost curve becomes tangent to the isoquant. Now, from geometry, you might recall, what is the condition of a line being tangent to a particular curve? Mathematical terms and geometric terms, maybe you'll recall it from your calculus. I want you to think back to calculus or geometry. Think back then and think about what is the condition for a line being tangent to a curve? Yeah, line would touch exactly at one point on the curve is exactly right. And even better answer is they will have the same derivative that I just saw in the chat. So thank you. Thank you for that. So yes, that's exactly what should happen. To find out where a curve, where a line is tangent to a curve, the slope of curve at that point. So if you take, for example, so let me type that out. Derivative of the curve equation is equal to right? So what has to happen is that the derivative of the curve equation has to be the slope of the, or the isoquant curve equation, I should say. Derivative of the isoquant curve equation should be equal to the slope of the cost curve. Okay, so if you can write down the equation of the isoquant somehow, and then cost curve is just a straight line, right? Cost curve, the green lines are just straight lines. So slope of that would be constant. Okay? And now how do you find the slope of this isoquant? You'll need the equation. And then remember when you write the equations, so this is your x-axis and this is your y-axis. Okay? So as long as you know which is your x variable, which is your y variable, you can find what is dy over dx. Okay, dy over dx will represent the slope for the curve. And if you have a line equation in x and y terms, you can also find the slope of that line. And you should be able to derive that. I'm giving you this hint and all this information because that's exactly what you'll need to solve your homework problem for the coming week. And then obviously you can represent them with X or Y, or you can say L here, the labor on the x-axis, and capital C on the y-axis. So in this case, you will be looking at dc over dl, okay? Because dy over dx, y-axis is capital, x-axis is labor. So instead of saying dy over dx, how we represent the derivative, we'll just call it dc over dl. Or you could call it y over x, it doesn't matter. But again, ultimately, you'll have to write those equations in C and L. And once you know C and L, you just have to find dc over dl, which is the derivative. And then once you have the derivative, you might have to equate to that to the slope of the line. Okay? And again, don't worry too much about it. I'll be happy to help you with the homework problem if you need assistance, but something for you to think about. Okay, but the key question is, if you want to find the expansion path, that expansion path lie where DC over DL becomes equal, DC over DL for the isoquant is equal to the slope of the cost curve. Now remember, the slope of the line with cost 300, 400, and 500, they're all the same. You see that? They're all parallel lines. So parallel lines obviously all have the same slope. So remember this discussion, or go back to it in the YouTube video. And that will happen around maybe around 15, 18-minute mark. So go back to the 15, 18-minute mark of this video, and then you can figure out what you need to do for your homework problem. So at least give you a substantial amount of it. Any question about this? Pause the recording. By changing, now what we can do is that if you change the axis, instead of having dollar and capital as your dollar and capital as your X and Y axis. Now, if you change the axis and you put kilometer of road on the X axis and cost in dollars per day on the Y axis, now you can take the point that you saw that I highlighted in blue in the last slide, these 3 points right here. These 3 points. If you take these 3 points and draw them out into a new curve with a different axis, you can get this as output of road 1 to 1.5 to 2 kilometers. This is 1 kilometer of road, 1.5 kilometer of road, and 2 kilometers of road, and then 300, 400, and 500. And you can join these points to get what we call the expansion path, converts to a total cost function. So this is what we call the cost function. Because in the cost function, we have to have a cost versus the output. And that's what we've got now. So now let's do this. Cost function. Let's learn about cost functions a little bit more. Cost function derivation applies for both constant and variable prices. The price, even if the price varies with resource quantities utilized, then your cost function just won't be linear anymore. It'll have different shapes. Now, you can do this derivation when prices don't really reflect the resource cost to the economy. Like we saw the example where you might be paying some workers some money, but then you're making that money back in the form of the profit that you get from selling those same workers their place to live, or having supermarkets where you sell food to them and whatnot. So you could do the same type of analyses, but that analysis, if you can't actually make it meaningfully, you cannot actually make it meaningful correlation between cost and the prices, then it's not, the analysis is not really meaningful. You don't really get how much quantity you should produce. But I think if you can, in fact, convert them into good dollar amounts, solid dollar amounts, then you can, in fact, make that connection. Cost functions, like production function, exhibits 3 fundamentally different kind of behavior. One is constant return to scale, economy of scale, and then diseconomy of scale. So let's show you all these 3 cases. So constant return to scale means your total cost function is completely linear. Your cost goes up in the same proportion as you increase the output. I did talk to you about how do you find the average cost and the marginal cost? Remember when we were talking about APP, average physical product, and marginal physical product? How do we find the average and how do we find the marginal cost? Anybody remembers, if you know the total cost curve? Maybe you learned that somewhere in microeconomics, somewhere along the way. Does anybody recall, if you know the total cost curve, like the one on the left, how do we go from the curve on the left to curve on the right? How do we go from the curve on the left, which is the total cost curve, just a straight line? As the output increases, the total cost increases in a linear fashion. How do you go from this total cost curve to the marginal cost curve? I'm going to pause the recording for a second, give you a chance to think about it. So yes, what I've heard in the chat is that if you take the slope of this curve, that gives you the curve on the right. But it's not entirely accurate. In this case, it might work. It's not entirely accurate. So my question to you is, if you just take the plain old slope of the total cost curve, and let's call it dc over dz, right? dy over dx, like that, dc over dz. If we were to do that, does that give you average cost or does that give you marginal cost? Okay, well, taking the derivative of total cost actually does not give you average cost. It gives you marginal cost. Remember, there is a difference between an average and a marginal cost. And it's very related to what we talked about. You can sort of almost see the connection between the two. The average cost and average physical product that we talked about, and then the marginal physical product. Remember, average is the aggregate average cost of producing one unit, right? And the marginal is the cost of producing one additional unit. And actually, if you take the derivative, and in this case, the derivative would be dc over dl, or I'm sorry, dc over dz. If you take dc over dz, which is going to be the derivative, that gives you what we call the marginal cost. That is cost of producing one extra unit. Okay? So the answer that I received in the chat was not quite correct. The correct answer is, if you take the derivative, you get the marginal cost. So now the question becomes, then how do you get the average cost? How do you get the average cost? Actually, to get the average cost, all you have to do is go to any point on this curve. And then let's find this value. Let's say if this value is Z1 and this value is C1. Go to any point on this curve, okay? And all you have to do really is the average cost is nothing but C1 over Z1. So it's the slope of the line. So just a straight line. So if this wasn't a straight line, that C1 over Z1 would in fact represent the cost, like the slope of the line joining your total cost curve to the origin. Yeah, y over x is exactly right. So I just read in the chat like so y over x is exactly right, or you could see C1 over Z1 in this case. So any particular value of output, you can get the average cost by taking the total cost and dividing that by Z1. But if I look at the curve on the right, or the graph on the right, what do I see? I actually don't see two different curves, right? How many curves do you see? In fact, all I'm seeing is this one line that I just annotated with blue. Because in this case, when you have constant returns of scale, because your total cost function is linear, the average cost is the same as the marginal cost. Even though conceptually they are different, but in this special case, where total cost function is a linear function, that tells me that my average cost and marginal cost is always just equal. Even though conceptually they are different things, but their value is always going to be equal. So in this special case, AC is in fact equal to marginal cost. Any questions about this? This is a very important concept to grasp, actually. The whole economics of this thing. This is a very, very important concept to grasp. So if you're not confused, if you're foggy about any of it, please let me know. Because I'm not seeing any questions here, I'm going to try to move on to the next slide. Oh, now I have economy of scale. My total cost curve now on the left is not linear. Now average cost and marginal costs are going to be different. And then you'll see that they're not going to be constant either. They're not going to be just one flat line at all. Okay? And why is that? It is so because remember, marginal cost is this right here. I'm going to draw some annotations. So if I want to find the marginal cost, okay, these blue lines are how I'm going to get the marginal cost. Okay. These blue lines, so it's basically, I'm essentially drawing at these different points, I'm drawing tangents to the curve. I'm drawing tangent to the curve here, tangent to the total cost here, and one tangent to the total cost here. And I'm measuring the slope of these blue lines, and I'm figuring them here. And that's how I'm getting this marginal cost. Now the question is, how am I getting the average cost curve in this case? It's obviously not the same as the marginal cost curve. If it's not, then how am I getting the average cost curve in this case? I just told you, you're getting the marginal cost curve by taking the derivative of the total cost function, dc over dz, at different points of output. Question now is, how do I get the average cost curve? That's exactly right. What I heard on the chat was that all you have to do is obviously get rid of these blue lines first. So I'm going to clear all these annotations. And instead of having the slope of individual points, I'm going to pick a point on the curve. So let's say I'm going to pick this point right here. And then I'm going to draw a line that goes from this point to the origin. I'm going to get the slope of this line. Okay, so that's one point will give you whatever is the slope of this line right here, the blue line that I just drew, the blue sloped line that I draw. So I'm going to get C over Z for that line. And that gives me 1 point of my average cost curve. So maybe that gives me, if I'm drawing it to scale, this point on the average cost curve. I could do the same thing for this point. I could do the same thing for this point right here. I'm going to draw a line that joins this point to the origin. I'm going to try to use a different color now. I'm going to join this line to the origin. And then I'm going to find what the slope of that line is by measuring C over Z over there. And that probably gives me maybe this point of the curve. And then that's how I'll do it. And I could do it for all possible points. So it's the slope of the line joining the origin and any point on the curve. So average cost is always slope of a straight line. A straight line slope joining from that point to the total cost curve point, or for origin point to the point on the total cost curve. Okay, now obviously this is pretty clear. Now the question is, why do we call it economy of scale? The idea of economy of scale is that if you produce more of something, you don't have to spend as much money. So why do we call it the economy of scale? If you look at the average cost curve and the marginal cost curve, you should be able to think about, why do we call it economy of scale? The idea of economy of scale is that if you produce more of something, your unit costs come down. Is that what's happening here? Give you a minute to think here. Okay, so why is this economy of scale? The idea of economy of scale is that as a manufacturer, your cost actually comes down as you produce more of something. Your unit costs come down. And that's what we call economy of scale. And you can see that the one big difference between the two charts is that on the left, you have total cost on the y-axis, but on the right, you have the unit cost. And you could see the unit costs come down, the average cost comes down as you produce more output. The unit cost actually comes down, right? That's a good thing. That means you're spending less to get more output. You're maybe spending a little bit more, but that is more than sufficient to produce more of the quantity. And that's why it's called economy of scale. Now let's think about what happens in this economy of scale. This is what your total cost curve look like. And then this is what your average cost and marginal cost curves look like. What I want you to do is think about, how do I get from the total cost to the marginal cost? The same ideas. How do you get the marginal cost curve? And how do you get the total cost curve? Or I'm sorry, average cost curve. Same exact ideas. So if I take the derivative, what would I get? The MC curve or the AC curve? So I take the derivative, that's right, I will get the MC curve. Right? If I take the derivative. And then if I take the slope of the line joining the origin to any point on the curve, I'll get the average cost curve. If I keep doing it for different outputs, I'll get the AC curve. I hope that much is clear at least. Now let's think about, why do we call it diseconomy of scale? Means as you produce more, your average cost, what happens to your average cost if you produce more output? What happens to your average cost if you produce more output under these circumstances? I have something in the chat. Yes, it increases. That's exactly right. Your average cost is going up. If you look at this curve here, the average cost is in fact shooting up as you produce more output. And that's the problem. right? As you produce more output, you don't want your average cost to go up, because that means what you have is diseconomy of scale. Means producing more is not really benefiting you too much. So let's see. So we already talked about these concepts. One thing is that sometimes the marginal cost curve could be discrete in nature. So we talked about the derivative being the marginal cost function, which is this formula right here, the derivative formula. However, if you have discrete outputs, you might also be able to use this formula if you have discrete output rather than a continuous cost function that I showed you before. Okay, it's basically the total cost of producing Z plus 1 units minus the total cost of producing Z units of output. Make sense? Questions? Any thoughts on questions? And then obviously average cost is the Y over X, total cost of producing Z units divided by the number of units produced. That's easy enough. And then two ideas of marginal cost. One, which is a continuous cost function versus when you have, so this is when you have a continuous cost function. And then this is when you have so under both circumstances, you could define which formula to apply. Questions? Okay. No questions, we can move on. Next slide. Obviously, we can construct the average cost and marginal cost curve from the total cost curve. We just saw that, we talked about that in detail. And this is what we call the unit cost. So both average cost and marginal costs are unit costs. Cost of producing 1 unit. One is the average cost, and one is the marginal, meaning cost of producing 1 additional unit. Now, this is interesting because treatment of fixed costs could make the whole difference. In the short run, transportation cost analysis, we usually consider cost function which could have 2 different shapes. One is with the fixed costs omitted, and one with fixed costs included. Now, this is important because let's say you're a transit agency. Sometimes you don't worry about the fixed cost. Because the thing is, in transit industry, a lot of time, what is your fixed? So what is an example? So let's first kind of come back to the question of what do we even call fixed costs? What are the fixed costs for a transit industry or a transit company? So the response I got in the chat is the cost of buying the bus. Yes, that's exactly right. Even before you've moved 1 passenger, you're going to have to buy the bus. So that's the fixed cost for a transit company. And sometimes, and you might be wondering, why would we ever want to exclude the fixed cost from our analysis? You might want to exclude because that might be coming from a different revenue source, or maybe it's a different grant money that you apply for to get the buses. So yeah, sometimes it does make sense to exclude the fixed costs from your analysis, even though obviously if you're talking about building a factory, it'll be foolish to not consider those costs, but in the purview of a transit company, sometimes it's okay to do so because your revenue stream might be completely different. And you have to just sort of worry about the variable costs and recouping some of those variable costs through Farebox, for example, right? So both of these types of analysis, fixed cost omitted and fixed cost excluded, they're both important. So this fixed cost omitted and fixed cost included, both types of analysis are included. And obviously we know what they are. They're the front end costs which must be incurred in order to produce the first unit of output. That's just one sort of textbook way of defining it. So we saw this economy of scale function, right? We saw this economy of scale function. And this is something that you've seen before. We just saw it a few slides ago. And let me see if I can pause the recording and have the students try to do annotation on my screen. So I'm going to pause the recording for just 1 second here. So one of the students was able to draw this curve right here if the fixed cost were not omitted in this case. So, and obviously the difference between the total cost curve with fixed cost omitted and fixed cost included at the very beginning, that line or that difference amount accounts for the total cost, or I'm sorry, the fixed cost, the cost of building a factory or whatever, right? Now the interesting question is, what does it look like? What does it look like in terms of the marginal cost and average cost? And I'll give you a hint. One of these curves, the marginal cost curve or the average cost curve, one of these curves will look exactly the same. It won't change. I won't change a thing about that curve. Which curve do you think would remain identical even if you do include the fixed cost? I see some responses in the chat already. Yeah, the marginal cost curve would remain the exact same. Why? Because remember, marginal cost curve is just a derivative, right? It's just a derivative of the total cost curve. So even if you move the total cost curve up, you're basically moving it parallel to what it used to be, and none of the slopes of the tangents are going to change at all. So yeah, that's right. The marginal cost curve remains the same, even if you include the fixed cost. So MC remains the same, even with fixed cost. Make sense? Everybody following this? Any questions? Now, if you're clear about this, that the marginal cost will remain the same, even if I add the fixed cost in my analysis, so I'm telling you the average cost will change, average cost function will change. How would that change? How would your average cost function change? What might that look like? It's a very interesting question. Where would you start your average cost function, first of all? Go back to the definition of the average cost. I'll give you that hint. So let's go back here. Let's go back here to my previous slide where we were talking about the average cost. And to get the average cost curve, I told you that you draw a line joining the origin to the point on the curve and take the slope of that line. And so let's go to the next slide and take advantage of the annotation that Abigail had created. And let's take that. And what she had created, if you do include the fixed cost in this mix, This is what the curve might look like. And if I want to find out the average cost curve, here is what I'll do. I'll take the origin, draw a line joining the origin to that curve, and get the slope of this line. What is in fact the slope of this line? What is the slope of this line? The line joining the origin point to the new total cost curve when we include the fixed cost. What is the slope of this line that I just drew? And I'm going to change the color. That helps. What is the slope of this line? Oops, I have the same color still. What is the slope of line joining the origin to the point on the curve? Slope is undefined or infinity, right? Because slope of y-axis is actually infinity, because this is a line parallel to y-axis, or it is the y-axis. So essentially, what happens is your average cost curve will essentially be starting as an asymptote and coming down as you move forward. So this is where your curve will start. It will be an asymptotic line to the y-axis and then just come down accordingly. Is that clear to everyone? And I want to show you that to you in the next slide when you do include the fixed cost. So this curve will actually start. So your marginal cost curve will remain the exact same, but your average cost curve will start to come down, come down, come down. And this point where average cost and marginal cost are equal, they could be interesting points. You know, they could be somewhat interesting points for us. That we are sometimes interested in study. But this curve will start here. But in fact, if you were to extend it, this will essentially be an asymptote to the y-axis like that. It approaches the y-axis forever and then comes down, comes down, comes down. And the point where average cost and marginal costs are equal is some time of interest. We can talk about that. But is everybody clear on how the presence or inclusion of fixed cost in your analysis affect your unit cost function? It does not affect the marginal cost function because cost of producing one additional unit remains the same. However, the average cost function starts at infinity and comes down as you produce more units. Questions? Questions? Okay, very good. So if you want to sort of get the definition, when the marginal cost is greater than the average cost, you have diseconomy of scale. If marginal cost is less than average cost, you have economy of scale. If marginal cost is equal to average cost, then you have constant returns to scale. So what you want to do is you want to operate in this regime, marginal cost less than average cost, you want to keep producing more, and you want to reach this point, MC equal to AC point, and sort of at that point, producing more unit is not that helpful to you. Because also you can see that after this point, the average cost starts to rise as well. If you look at the annotation, if I want to create an annotation here, you could see that beyond this point, the average cost starts to rise. So you basically want to operate right here at this point. Does that make sense? Questions? Because once you pass this point, your economy of scale becomes diseconomy of scale. Any questions about this? There are no questions. Let's talk about why do we, in fact, get economy of scale? Economy of scale could come because there is fixed cost, right? Once you build the factory, you might as well produce something. So there is economy of scale because you're recouping your fixed costs at the initial part. Because if you're starting an infinity, obviously that will be more than marginal cost, right? So MC will be greater than AC, or sorry, MC will be less than AC if you're starting with a fixed cost, because your AC curve will start at infinity. So obviously it's higher than MC. So that means you'll have, if you account for fixed cost, you always start with economy of scale. However, there could be external cost effects. So sometimes if you, like Costco, if you buy more, you get some discount. So if you buy in bulk, you save some money. So there could be some external cost effects. And some increasing return in production due to ability to use more efficient technology. So you could have, like, you could use bigger machinery that can produce more things at a lower cost if you're building enough things, right? So that's some of the reasons why economy of scales might exist. Why do you think, can you think of some reasons why this economy of scale may exist? So when you produce more, it costs more. Any thoughts on why this economy of scale might persist? Yeah, scarcity of resources, maybe poor management and organization because you're not good enough at managing a bigger enterprise. That certainly is true. And then resource prices could be, so onset of, and then, so basically the management problems, you can call it system breakdown as capacities approach, adverse price effect due to resource limitations. So yeah, if you have, like, for example, PG&E, the power company, they charge more money if you use more electricity. So that's your diseconomy of scale. If you try to produce more, then some of the resources become more expensive. And then this one, we see it in traffic congestion all the time. Onset of congestion as the capacity is approached. Yeah, you can add more traffic to it when you're trying to get from level of service C to D. You can push more traffic. But if you go certain more demand, then you are at like LOS. So it's easy to switch from LOSE to LOSF. So there is onset of congestion as capacity is approached. So then you're not able to push as many people, as many cars or whatever you're trying to push through your system. And that could create diseconomy of scale. So that's fairly common in the transportation system to have that diseconomy of scale. Now let's think about a little bit, not too much, but a little bit about long run cost functions. And I just have like a couple of slides left. So we're getting close to wrapping up this lecture. What do the long run cost function look like? And I drew them out here. Why do we need, first of all, why do we need long-term cost function? So I'm gonna pause the recording here. So the long-term cost functions might be needed if the technologies evolve over time. And then you no longer have just one technology, but multiple technologies in place. And you can switch factories over if you need to produce more. So as output changes, as the amount of output changes, you can operate on different cost curves because you could change over into different factories. So then how do you actually define a cost curve that is, if you have these total cost functions, how do you actually use these? Let's say if you have TC1 and TC2 and TC3, there are 3 different short-term cost functions. What's the best way of combining them? The way to combine them is very interesting, is that what you do is you take the most favorable portions of the short-run cost curve. You take the most favorable portions of the curve. And what is the most favorable portion of the curve? It's the portion where average cost curve is coming down. When average cost curve keeps coming down and does not increase. So basically you find out, okay, what's the lowest average cost curve for the first one? Okay. And then you take that, and then as soon as that starts rising, you switch over to the second cost curve. And then you try to operate on that curve. And then when that starts rising, you switch over to the third curve. Okay? So you go to the point where the average cost curve starts to rise, where it turns its shape. You go to that curve and you go up till that point on the short-term cost curve, and then you switch over to the next one, and then switch over to the next one when that starts rising. So you take the most favorable segments. So most favorable segments are typically the ones where average cost is still going down, down, down. But then when average cost curve starts to rise, you switch over to this next curve. And then you switch over to the next curve when that one starts to rise. So long-run cost functions are typically represented as average cost relationships. If properly constructed, long-range cost curves show the cost of operating the most efficient technology for each level of output. If you're constructing properly, long-range cost curves show the cost of operating most efficient technology. So as I said, you could change factories if you'd like. So most efficient technology for each level of output. Some technologies that are not at all financially reasonable, you can include that. Perfectly divisible technologies idea, it's like you have infinite number of short-run cost curves. And then you could, but typically that's not the case. So that's almost never the case. Perfect divisibility is very, very rare. So long-term cost curves won't be like continuous curves. They will be discontinuous curve, and that they'll be like a little bit wavy in shape. Okay, because you're not going to have these continuous curves. You're going to have a limited number of total cost curves. Perfectly divisible technologies are mostly theoretical, idea. They're not sort of any idea that works in practice. Okay, so that's your idea of the long-run cost functions. With that, I'm going to just show you quickly what your homework problem would look like, and that's one of them. And this is related to this lecture. And this Q equal to L raised to power half and C raised to power half is your production function. So based on that, you will have to create some isoquants. And then I give you unit price of labor and capital. Okay. And your job is to develop that cost function that expresses the relationship between the number of vehicles produced and the total cost of that production along the optimum expansion path. Okay, so I won't belabor this right now, but I would like you to think about and go back to the slide here. Go back to this slide and the discussion that we had. And this will be around 18 to 20 minutes of this lecture, maybe 15 minutes into this lecture, you will find that discussion. So I'd like to maybe you to rewatch that section of the lecture and then try to see if you can work out this problem. Okay. And I want you to have a theoretical relationship and then do it in Excel as well. And I will have I'll assign this homework problem tomorrow on your Canvas page. So there will be some more information about this, and then make sure that you work that out. Okay. I don't have anything else to add to the lecture. If you have more questions, please let me know. Other than that, you're free to leave.